So I plan to talk for about 20-25 minutes and then take questions. If you have a question that you cannot wait to ask, just raise your hand, and as long as there aren't too many interruptions, I can take a few during the presentation. So what I'm going to talk about today is joint work with another colleague from Krannert, John McConnell, who is also a professor of finance in the business school. Just to introduce the topic a bit, the idea goes as follows. So in the last 5 to 10 years, smartphones and their apps have become incredibly common. And as with many other technological advances, they have improved our lives in many ways. This, however, has not come without some costs. And so in this paper, we are going to focus on one specific cost associated with smartphone apps, and in particular associated with using smartphone apps while driving. So we are going to focus on the human cost and the economic cost of doing so. And we are mostly addressing a couple of questions in our research paper. So the first is whether using smartphone apps while driving has given rise to an increase in vehicular crashes, injuries, and fatalities. And the second is to the extent that this has happened, then what is the economic cost that we can associate with this increase in crashes, injuries, and fatalities. To put these questions into context, I will show you a few numbers that we got from official sources. So the first is numbers about crashes and fatality crashes. These are all vehicular crashes. So until 2011, in the previous 25 years, crashes and fatality crashes had been declining. This decline has been quite steady, although not uninterrupted. But starting in 2011, things started reversing course. Both crashes per year as well as fatality crashes per year have started to increase. With the result that we observe in 2016, the last year for which official data are available, in which the number of crashes is actually greater than it used to be in the 80s, and fatalities are quite a few more than they used to be in 2011. This increase in fatality crashes has been widely documented in the press and commented upon. Press articles have often tried to attribute this increase in crashes to cell phones, but obviously cell phones are nothing new in 2011, and they haven't become much more diffused between 2011 and 2016 than they were in 2010. What has really changed is the diffusion of smartphones and their apps. And so these are some numbers that we downloaded from Wikipedia about downloads of apps, either from Google Play or from the Apple's App Store. So there is a potential correlation between the increased use of smartphone apps and the increase in vehicular crashes. But obviously, it's very difficult to make a strong argument, even just about a correlation from those couple of numbers. For sure, the press, as well as insurance companies, have attempted to attribute at least part of these increasing crashes and fatality crashes to smartphones. For example, there is an article in one of the 2017 issues of the Wall Street Journal pointing out that insurers have justified, at least in part, the increase in insurance premiums that have occurred between 2011 and 2016 to smartphones. But the same article recognizes that it's, however, very difficult to establish a very clear causal link between smartphone usage and crashes. So in this paper, we are going to circumvent this difficulty in establishing a very clear link between the two by exploiting the introduction of one specific app which has some features that are very useful from a scientific standpoint. So the app in question is the very popular game, Pokémon GO, which those of you who are familiar with the game know presents some activities that can only be performed at specific locations, but not at others. Now, for those of you who are not familiar with the game, I will actually give you a little introduction to the game, and then I will explain what we did in the paper with this game. So the game is a location-based augmented reality game that you can install in your smartphone. It was introduced on a very specific date, which is July the 6th of 2016. The game was an incredible success in terms of number of downloads and the number of active players who were playing the game in the following months. And so estimates point to about 100 million downloads by the end of the month in which the game was introduced, which is obviously a huge discontinuity from the month of June, in which the game was unavailable, to the month of July, when the game was introduced. So one possibility is that users of the game might be using the game while they are driving their car. This is actually certainly the case, at least in some cases. The press has documented crashes due to people being distracted by using this game. So the game works as following. A player, after they install the game, will try to capture these creatures known as Pokémons, which appear on the smartphone, on the screen of the smartphone. To capture these Pokémons, the player needs to have some weapons. The weapons have a name, which is Pokéballs. These Pokéballs can be bought anywhere, so you can buy some Pokéballs as I'm presenting, or they can be downloaded for free, but only in the vicinity of places known as Pokéstops. These Pokéstops are actual physical locations in the proximity of which it's possible to download these weapons for free. These weapons can then be used to capture the Pokémons, which is the goal of the game. So these locations will appear on the virtual map associated with the Pokémon GO game to the extent that you do launch the app on your phone. And as you start walking around, this map will reflect your surroundings. So for example, it may show State Street. It's going to show this building. And then it will show, if there are Pokéstops nearby, icons that do represent these Pokéstops. As you walk around, this virtual map will have you move along the actual route that you are walking or driving. So as a player, if you want to download these weapons that you will need to play the game for free, what you can do is approach the Pokéstops. This can be done either by walking or by driving, or if you are fortunate, you might have a Pokéstop nearby your office or nearby your classroom, in which case you can just be sitting and download these weapons. To download the weapons, you will need to tap the icon of the Pokéstop and then swipe it. It only takes a few seconds, so this is an activity that can plausibly be done while the player is driving, as opposed to be walking or just sitting. In order to download these weapons, the player needs to be close enough to these Pokéstops. In practice, that means that the player needs to be approximately within 50 meters of a Pokéstop to be able to download the Pokéballs successfully. Collecting the Pokéballs or tapping and swiping the screen to collect the Pokéballs is not the only type of activity associated with getting these weapons. The player also needs first to turn on the phone. Then they need to activate the game. And if for any reason their screen has locked, they will also need to unlock the screen. So there are a number of activities that are needed to be done in order to successfully download the Pokeballs, but the intensity of these activities will increase as the player gets closer to the Pokestop, at which point they can finally download these Pokeballs. So our hypothesis that we have behind our tests goes as follows. So if it is true that the player is playing while driving, and if it is the case that using apps while driving gives rise to an increase in crashes, we should find a disproportionate increase, a greater increase in crashes in the vicinity of Pokestops, because in the vicinity of those locations, there are more distraction-related activities that can be performed as compared to locations that are not in the vicinity of Pokestops, where all these activities cannot be performed. So to test our hypothesis, we are going to use some data. There are two main pieces of data. One is data on crashes. So we got data on all vehicular crashes that occurred in this county, Tippecanoe County, between March the 1st, 2015, until November the 30th of 2016. So we have a few months after the introduction of the game and quite a few months prior to the introduction of the game. We got the data from a variety of police departments and the sheriff office of Tippecanoe County, which we obviously thank for sharing the data with us. The data include things such as, for example, the location of each crash that was reported to the police. The location includes the name, the street name where the crash took place, perhaps the intersection in question. It does include the specific geographic coordinates of the crash. The coordinates are going to be very important because they will allow us to establish whether it's possible that the player was playing a Pokemon GO while driving when the crash occurred. Essentially, collecting the Pokeballs can only be done if the player is close enough to a Pokestop, and so we are going to use geographic coordinates to determine whether the location of the crash is close enough to a Pokestop so that it's plausible that the player, the driver, was playing the game when the crash took place. The police accident reports also contain a lot of additional information, which we are going to use in our analysis, including, for example, if there are injuries, the number of people injured. If there are fatalities, unfortunately, we would know if somebody, unfortunately, has lost their lives. The second piece of data is the location of these Pokestops. I've talked quite a bit about them. We want to determine whether a crash occurred in close enough proximity of a Pokestop so that we can tell there is likely a connection between playing the game and the crash occurring. So we obtained the data on the coordinates of Pokestops and also other locations associated with Pokemon GO from Science Hub, which we also thank for sharing the data with us. Just to give you an example, I went to the webpage of Science Hub, and I took a picture of the map that surrounds this building. So this is West State Street, and we are located approximately where that red rectangle shows up. In this map, these blue things that you see, those blue cubes, are Pokestops, for all of which we do have the exact coordinates. And those pyramids, orange pyramids, are other points of play known as gyms. So what we do in the paper, again, is to try to see whether there is a disproportionately greater increase in vehicular crashes, injuries, and fatalities in the vicinity of Pokestops versus other places that are not in the vicinity of Pokestops. Okay, if, again, a player was playing the game while a driver was playing the game while driving, and this playing games while driving gives rise to increase in crashes, then we should find a greater increase in crashes in the proximity of Pokestops. So just to give you some idea about crashes in Tippecanoe County, So during our sample period, there are about 11,000 for which we have the precise coordinates of the location of the crash. 8,500 of these occurred prior to the introduction of Pokémon GO, and 2,800 or so occurred on the date of the introduction of the game or in the following approximately 5 months. You notice that there are more crashes prior to the introduction of Pokémon GO than after, but this is only because we have many more days pre-Pokémon GO of data than post-Pokémon GO. So we have data on crashes for the 493 days that preceded the introduction of the game, and we have data on crashes only for the 148 data that follow the introduction of the game. So if we want to get a first sense idea about how crashes, the intensity of crashes has changed, what we can do is focus on crashes per day in order to make a more appropriate comparison. And so here it's clear that prior to the introduction of the game, during our sample period, there were 17 crashes per day on average, with some rounding. After the introduction of the game, there are 19 crashes per day. So it's more than a 10% increase in the number of crashes per day. Whether that's a lot or a little lies in the eyes of the beholder. In my opinion, a 10% increase in the number of crashes is actually a pretty large number. Now, in our tests, we cannot just compare the number of crashes over time, because over time, a lot of things change on top of the introduction of the game. For example, the price of gasoline was almost certainly different on November the 30th of 2016 versus November 30th of 2015. The economy was doing differently at the different points in time. So all these things would contribute, for example, to having more or less people on the road, which would also correlate with the number of crashes. So to make a more precise comparison, we are then going to split the data even further, compute crashes at locations that are in the vicinity of Pokestops and crashes per day at locations that are not close enough to Pokestops, so that it's not plausible that the player was trying to collect Pokeballs. So to do so, essentially what we are going to do is for each location, where a location is a pair of coordinates, so a spot where at least one crash occurred during our sample period. The crash might have occurred prior or after the introduction of Pokémon GO, but it's some spot likely on a road, so that it's reported to the police. So for each one of these locations, on each day, we are going to count the number of crashes, vehicular crashes. We are going to count the number of crashes that involved injuries and the number of fatalities, if any. Just to give you an idea, if we divide these 17.25 average crashes per day pre-introduction of the game by the number of locations in which at least one crash occurred during our sample period, we get 0.00366 crashes per day at a given location. That simply means that on this specific spot, most of the time, most of the days, no crash occurs. But occasionally, there is one. So I will show you some very simple statistics that are going to hopefully help those of you who are not in academia and don't want to focus on very complicated tables that only a crazy professor would put together. And so this table reports the average number of crashes per day at variety of locations, of which there are two types. One are locations that are close enough to Pokestops, so where it's possible that the player was playing the game when the crash occurred. And the second set of locations are all those other locations where some crash occurred at some point in time, but those locations are not close enough to the Pokestops. So at locations close to the Pokestops, there are approximately, and the number doesn't really matter, 0.004 crashes per day pre-game. And after the game is introduced, this number becomes greater, 0.005 5, 5. Okay, it doesn't take genius to find the second number greater than the first. We computed the difference, so this is by how much the intensity of crashes has increased at locations in the vicinity of Pokestops following the introduction of the game as compared to prior to the introduction of the game. And then we make similar comparison for locations that are not in the vicinity of Pokestops. And you will notice a couple of things. First, that there are few crashes at those locations on average, even prior to the introduction of the game. So there might be something special at those locations. They might be in corners where nobody drives or very few people drive, and therefore they are bound not to have crashes. The second thing that it's worth noticing is the change in the frequency of crashes or the number of crashes. And obviously this change at locations that are not in the vicinity of Pokestops is much smaller than the change that we observe at locations in the vicinity of Pokestops. So in the vicinity of Pokestops, there is much greater increase in crashes than at locations that are not in the proximity of these locations. So we can compute the difference in differences, which is gonna be what I'm gonna do next in a bunch of crazy tables. But the idea is to count, to determine by how much more the frequency of crashes goes up in locations where it's possible to play while drive versus locations where that's not possible. This increase in the number of crashes per day essentially corresponds to a total of 136 incremental crashes in the vicinity of Pokestops on top of what has occurred at locations that are not in the vicinity of Pokestops. So those are really additional crashes that occur only at those locations and only after the introduction of the game. So what we are going to do next is control for a variety of things, because you might have, I think, a couple of concerns. The first is that what we find is not due to Pokemon GO. It's due to something else. And so I'm going to spend a little bit of time to convince you that it actually has to do with Pokemon GO. And the second thing is that maybe it's not due to people playing the game while driving, which I'm going to address at the end of my presentation. So to account for the possibility that it may be something else to give rise to these increasing crashes, what we do, we run a regression, so more complicated analysis, in which we have controls that account for which day we are looking at. So if, for example, I didn't check online, but if November the 30th, 2016, the last day in our sample, corresponded with a day with a frozen rain, there might be more crashes because of that. So these location fixed effects account for anything that affects the whole Tippecanoe County equally at a given date. And then we have location fixed effects, which capture, for example, whether a given spot where some crashes have occurred is just across the street from a bar, rather than being in the proximity of a Pokestop, because perhaps at those locations, crashes occur for reasons other than the game. Importantly, what we also want to account for are things that change across locations differently through time. So a big thing here at Purdue is that many of you who I suspect might be Purdue students will not be here in the summer. The game was introduced on July the 6th, which is during the university break. So if it's true that students tend to congregate at locations that correspond to Pokestops, and the number of students around varies a lot through time, it might be that the results that I showed you in the previous table could be due to these fluctuations in the number of students that congregate around Pokestops through time rather than to the introduction of Pokemon GO. And so we are going to control for this by including some control variables. I will not get into the details. Our results remain pretty much unchanged. The difference in the differences between the coefficients, instead of being 0.00099, becomes 0.00097, barely a change after we control for all of these things. Second thing that I'm going to show you to convince you that everything is due to Pokémon GO is to narrow the period of our analysis. So we have a long period, almost 2 years. A lot of things other than Pokémon GO happened during these 2 years. But if we narrow the event window sufficiently, we will have only very few potential candidates for an alternative explanation of our results. If we can focus only on the second in which the game was introduced, obviously there is very little space for alternative explanations. Now, we cannot focus on a second because, fortunately, there are not too many crashes per day in Tippecanoe County. So if we were focusing on 1 second, there would be no crash. So we are going to compare the week that follows the introduction of the game with exactly the same week in the previous year. So we have a Saturday in the pre-period, one in the post-period, a Sunday in both periods. There is no confounding event such as July the 4th because we omit the week prior to the introduction of the game. We still find a disproportionate increase in crashes in the vicinity of Pokestops when we just focus on the week that follows the introduction of the game. Now, after we control for all these things we have in the regressions, we still have 134 incremental crashes that can be attributed to the introduction of Pokémon GO. These incremental crashes correspond also to 31 incremental injuries and 2 incremental fatalities in Tippecanoe County during this 148-day period that follows the introduction of the game. So yes, the introduction of the game was followed by disproportionate increase in crashes, injuries, and fatalities in the proximity of these points of play. Both John and I are economists, and so we felt the urge for attaching some numbers, some dollar numbers to our estimates of incremental crashes to tell how big of a problem this might be for people who are perhaps not using the game while driving. So obviously you may get injured because somebody bumps into your car. But even if you are not involved in a crash, there might be some consequences for insurance premiums, as the article from the Wall Street Journal was suggesting. And so we got an estimate about the incremental dollar value of the damage to the cars, which was obtained from the police accident reports. The police discloses an estimate of the damage to the cars. So because there are many more crashes, there is some incremental damage to the vehicles. Then for the people injured, we got 2 pieces of data. So from the Insurance Information Institute, we got data on the average claim for bodily injuries in the state of Indiana. So for each crash that involves an injury, usually people involved who suffered the injury on average submit claims for about $16,000. And then on top of that, there is an income loss from work, because people might have to miss days of work. And this might be actually covered by the insurance depending on the policy that the person has. And so the estimate of this loss of income at work is about $15,000 per person injured. So for a total of about $1 million of incremental costs associated to injuries during the 148 days that followed the introduction of the game. Now, attributing value to the human lives lost is incredibly difficult. In the paper, we try to present estimates using a variety of methodologies. Here, I will just stop saying that it's difficult. So I will ignore it in trying to determine what is the implied increase in insurance premiums. So we are just going to focus on the incremental damage to the cars and on the claims associated to the injuries. So to estimate what is the expected increase in insurance premiums associated with the game, we did a couple of things. First, we found out what is the average insurance premium in the state of Indiana. So the average annual insurance premium from, I think it was the Insurance Information Institute, is or was $730 per year. Then we divided this $1.5 million of claims by the number of people resident in Tippecanoe County of age 15 or greater. This is our proxy for the number of drivers. This proxy overstates the number of drivers for sure, which means that we are understating the increase in insurance premium. So we divided this $1.5 million of incremental filings by the number of residents in Tippecanoe County of age of 15 or more, and then divide this by the 728, which is the insurance premium per person. So this corresponds to an estimated increase in premiums of 3%, 3.3%. Again, whether that's large or not, that lies in the eyes of the beholder. This is assuming that everybody who has a car is going to share these increased expenses. We ran a number of tests in the paper just to rule out the possibility that our results are not due to people who are driving the car using the game. For example, a concern that was pointed out to us is that perhaps it's a pedestrian who is playing the game and then jumps in front of a car. They get injured, but there is a crash. It's reported to the police. So to address this concern, we excluded all the crashes that involved pedestrians. The police reports give us this information. Our conclusions are robust to excluding these crashes. So it's not, maybe there may be one or two that are due to pedestrians, but our results in general cannot be explained based on that story. Perhaps it's a passenger, like a parent driving with their kid. The kid is playing a Pokemon GO, and then they capture the Pokeballs as they drive by a Pokestop. The kid starts screaming of excitement, and the parent gets distracted and crashes. So in this case, the crash is due to the game, but it's not due to the driver playing the game while they are driving. So we exclude all the crashes in which the person causing the crash had a passenger in the car. And so we only focus on crashes in which there is no passenger, and therefore it cannot be the passenger giving rise to the distraction. Our conclusions remain. We also compare Pokestops with second set of points of play called the gyms, where people fight their Pokemons with Pokemons owned by other players. Fighting a battle gym takes several minutes, and during the entirety of which the player needs to be very close to the gym location. So because it takes several minutes of really snail speed moving, it's very much implausible that near gyms people engage in fights while driving. So if our crashes are due just to people driving to Pokestops and gyms, then parking, then getting off the car and playing, so the crashes are due to the increase in traffic due to people driving to those locations, rather than people playing while driving, we should find the same increase in crashes in the vicinity of Pokestops as well as in the vicinity of gyms. But we don't find anything in the vicinity of gym. All the results come from locations in the vicinity of Pokestops, which are the only locations where it's possible to do activities while driving. So to conclude, using these detailed police accident reports, we do document a causal impact of using smartphone apps while driving on crashes, vehicular crashes, injuries, and fatalities. We estimate the incremental cost, even excluding the cost associated, the value of the 2 human lives lost, to be around $1.5 million just for Tippecanoe County, just for the 148 days that followed the introduction of the game. And this figure translates into a non-trivial increase in insurance premiums. I'm done, so if you have any questions, let's see.
I think one of your bullet points had it, but I didn't hear you say it. Did in any of the data in the police reports support, of a finding? Obviously not every one of them would, but as we test the data set, did anybody comment in any of the incidents that yes, Pokemon was being played as a potential cause of this?
So the police reports are not super detailed in terms of cause of the crash, but they do report a primary cause, a secondary cause of the crash. We don't see specifically the name of a game or a specific activity in the police reports of Tippecanoe County, but we do see in the reports whether the crash was caused by the person being using the phone while driving. Using the phone while driving or playing a Pokémon GO while driving is not illegal in Tippecanoe County. For this reason, the police cannot actually check legally. But we do find a correlation between the increase in crashes in the proximity of Pokestops and the crashes attributed to distracted driving, including using cell phones, as reported in the police reports. In the press, there have been a few cases documented where people were explicitly reported being playing this specific game when crashes, including multiple people involved in the same crash. Yes?
So you said that with the Pokestop gyms, there's less crashes around them, and that players had to spend more time there. Would you think that putting more time at the Pokestops would probably reduce this? Like you would have to stay there for a bit to get the items?
It's difficult to tell. Possibly. I mean, something that would probably have the biggest effect would be to make it impossible to play the game while driving altogether. The developers of the game have moved a bit in this direction, and so they have introduced a speed limit above which it's not possible to undertake any activity. They have introduced warnings against playing while driving. So there are certainly some activities or some recommendations that can be made to reduce crashes.
So you mentioned that the study only goes until the end of November in 2016. If you had to estimate what the continuing cost would be after that, especially with the potential drop-off in popularity of Pokemon Go, do you think that we would continue to see similar effects of Pokemon Go while driving?
Yeah, I would expect the cost to be lower in the post periods, something I didn't have the time to discuss, but that we look into in the paper. Is the discontinuity or the change in the frequency of crashes over time following the introduction of the game as the popularity of the game drops. And so we find that as the game becomes less popular, there are fewer incremental crashes. There remain some, but it's fewer than in the first month or two. And so extending the sample period should plausibly give rise to a lower economic cost of the game per day.
I was just going to ask, why didn't you guys, or if you did, why didn't you present any data that you collected from the year before? I feel like that would help. Have any questions about like student congregation during the time, if it was to just, that's just correlation, or the fact that just a certain time of season. Like I was just thinking like, could you not have gotten a study from 2015 in the same month Pokemon GO was published, and then correlated the crashes from that time to when after it was published?
Yeah, we used a variety of sample periods, time periods, including the month of July 2016 alone versus the same month of the previous year. We asked the police reports data only starting March of 2016, because when we started the study, we didn't have any belief that we would need a longer time period. Obviously, the longer is the time period, the greater is the potential for something else giving rise to some of the results, so it's really not ideal. But we did make comparisons between the post-period versus variety of pre-periods as benchmarks, and the results are very, very robust. All right. Well, thank you, everybody.